Dear friends, welcome to my workshop. This is the third part of a short series of videos on the conversion of my Weiler lathe from DIN 800 screw-on spindle nose to a DIN 55027 short taper spindle head. In the first part, I manufactured basically a chuck flange for the original DIN 800 screw-on spindle nose of my Weiler lathe. As some kind of intermediate project, I machined the bayonet type disc in part 2. Now we are getting back to work on the actual spindle head by drilling the required hole pattern and turning the centering cone. As the final operations will be done with the head permanently mounted to the spindle, I will begin by drilling the holes. I start by mounting and centering the work on the table of the milling machine. Unlike the bayonet disc, no arc-shaped slots are to be milled here. Thus I can lazily make use of the DRO's hole pattern feature. The part is already centered, so I can leave the center position at 0, 0. The bolt circle diameter is 85 mm. We need 6 holes. Which are located on a full circle, which is from 0 to 360 degrees. Now I can select the hole to be worked on, and the display shows me the displacement between the current and the required position. I spot and pre-drill the holes as usual. The high-speed drill fails very soon. A high-speed drill with cobalt works much better. Remember, this is pre-hardened tool steel. These are the holes which will be opened up to 21 mm. The 12mm high-speed steel drill with cobalt works perfectly well. However, again, this 19mm regular high-speed steel drill fails after a few millimeters. Thus, I abuse a 14mm end mill as a drill. As there is almost no radial force, I for once get away with using the drill chuck. Apologies. The holes are bored out to 21mm. This takes time but works surprisingly well with a cheap Chinese freshly ground boring bar. The stop bolts will be mounted with M6 bolts. I drill 6.5mm holes for them. Counter bores for the screw heads are machined with a 14 mm end mill. The quill stop limits the depth of the bores. Now all that remains to do is boring a countersink hole and the thread to hold the driving stud. The position was calculated using basic trigonometry. The chuck side requires a counter bore into which the driving stud will be inserted. Actually, the button should be attached to the spindle nose by an M6 screw. However, I tried a couple of taps and failed to machine the M6 thread into the two-lock steel. So I went to plan B and machined a conical countersink which will accommodate the head of a screw. Unfortunately, I made a senior error and countersunk one of the holes for the stop bolts. This won't affect the functionality, but it dents my pride. Now, finally, it is time to mount the spindle nose onto the spindle. To be on the safe side, I removed the spindle from the lathe. I intended to install new spindle bearings and repair a damaged belt pulley anyways, so the effort was acceptable. The spindle is securely mounted between aluminium jaws in the vise of my milling machine. The original spindle nose is cleaned with acetone. I borrowed Mr. Crispin's toothbrush, don't tell him. I attached a long square tube to the new spindle nose which can be used to apply brute force if required, just to play safe. The interior of the new nose is also cleaned. I heat up the new spindle nose to approximately 100 degrees Celsius, as this is a light press fit with 5 microns interference. I use Loctite 648, which is a high-strength retaining compound for cylindrical fitting parts. The compound is suitable to bind press fits, in this case the cylindrical part of the spindle nose. It is also able to bridge gaps up to 0.15 mm. This is relevant in the threaded area. The assembly worked way better than expected. No issues here. What a relief. After the reassembly of the spindle, it is time to tackle the actual short taper. I started by turning the OD to approximately 120 mm. A worn insert makes spectacular fireworks. Nice for YouTube. A CVN insert is used to finish the OD with a few tenths of millimeters oversize. The inside of the spindle nose is bored out cylindrically down to the original spindle. Now I remove material to form a spigot, which will eventually form the tapered nose. The DIN 55027 specifies a cone ratio of 4:1 on the diameter, which is equivalent to a flank angle of 7.125 degrees. As I already put a lot of work into this project, I want to make 100% sure that my cone angle is set correctly and start by machining a cone as yet another test piece. My Weiler lathe has no proper work holding device right now. Thus I use my Emco lathe to machine a round bar with a spigot, matching the inner diameter of my new spindle nose with a tight press fit. The part is held in place with a makeshift drawbar. The compound slide is rotated to slightly above 7 degrees. With the correct compound angle, the difference between both ends should be 80 mm times sine of 7.125 degrees, which equals 9.92 millimeters. The compound slide angle is adjusted until I get this reading. However, I made a minor mistake here, as we will see later. The position of the top slide is zeroed on the dial, and I mark the position of the 80 mm interval with a pen. Here I have already removed some material and it is time to get rid of the chips. In order to be able to measure the cone accurately later, the first 80 mm are turned cylindrically using the carriage. Then the cone is turned using the compound slide. As soon as the diagonal length of the cone has reached 80 mm, a cylindrical section is turned on both ends. This allows to take exact measurements of the diameters of both ends, as long as a tool with a very small tip radius is used. In this case, I get a difference of 9.847 millimeters between the radii on both ends of the cone. This is equivalent to a flank angle of 7.07 degrees, which is below the required 7.125 degrees. My mistake? I forgot to adjust the plunger of the dial indicator perpendicular to the spindle axis when I set up the compound slide angle. So I have to readjust the compound slide and redo the turning operation and measure again. After this correction, the deviation of the flank angle is at 0.005 degrees, which is good enough for the short taper. I would like to experiment with another CBN insert and use it to face the mating surface. Usually you would grind the mating surfaces. However, I don't feel the need to do so, as the CBN tools create a beautiful surface finish. Now, time to turn the real cone. The diameter of the cone is determined with the help of measuring pins. Here I am using thread measuring wires. I will describe the method in more detail at the end of the video, including the calculations. All measurements are repeated multiple times and I use different pin diameters to check the consistency of the measurements. Here I am abusing spotting drills as measuring pins. I enter the measurements into a diagram as blue plus signs. The average value is entered as a red star symbol. The procedure is repeated multiple times, and I gain confidence as the measurements and the infeed values are pretty consistent. However, in the end, the diameter is slightly below the permitted interval. Thus I reface the flat mating surface with the CBN tool and remove just a few hundredths of a millimeter. This brings the diameter back into the allowed range. Machining and undercut is the final lathe operation on the spindle nose. The spindle nose is now finished, apart from the bolts and driving stud, which will be machined in another episode. And now, as promised, or should I say threatened, the description of my method to measure the cone diameter. So, if you are not interested in shop math, feel free to leave the video here. Let's have another look at the spindle nose. The cone diameter is specified at the intersection of the flat mating surface and the cone. In practice, it is impossible to measure this diameter directly because of the undercut, among other reasons. Therefore, I determine this theoretical diameter using measuring pins, which are in contact to the flat mating face and the cone. Naturally, the indirect measurement has to be converted into the real diameter. The following dimensions are known. The radius of the measuring pin R, the flank angle of the cone alpha, the measurement M. We are looking for the diameter D. Delta denotes half of the difference between the diameters M and D. Let's take a look at the following triangle to find delta. The long side is equivalent to the radius of the circle or the measuring pin. Let's call the vertical side A and the horizontal one B. A and B can be calculated as R and alpha are known. A equals R times cosine of alpha. B equals R times sine of alpha. Now the position of the contact point between the cone and the pin is known. Let's have a look at another triangle in order to find the intersection between the face and the cone. The length of the horizontal side equals the radius minus the known length B of the blue triangle. That is R minus B. Now we have to find the length F of the short side. Both triangles are mathematically similar. Thus the ratios of all corresponding sides are equal. That is, F divided by R minus B equals B divided by A. Solving for F results in F equals R minus B times B divided by A. Delta can be calculated from the now known lengths R, A and F. Delta equals R plus A minus F. Inserting F into the equation gives the left-hand expressions are brought to the common denominator, a. A square plus b square can be reduced to r square. R can be factored out, and again. Using the trigonometric functions for a and b, cancelling out r gives the final formula. Let me finish with an example. The radius r of the measuring pins, a spot drill in this case, is known to be 4.004 millimeters. The cone angle alpha equals 7.125 degrees. Putting these values into the formula gives delta equals 7.5387 millimeters, which results in the cone diameter d equals m minus 2 delta equals 78.641 millimeters minus 15.077 millimeters equals 63.564 millimeters. That's it for today. In part 4 I will machine my first chuck flange with lock studs and a few small parts like the stop bolts and the driving stud. Thanks for watching and your patience. I hope to see you in the next video. Again, ganzer Abschnitt nochmal. However, again, this 19 mm regular high-speed again. The spindle is securely mounted with again. I borrowed Mr. Crispin's tool again. A worn insert again.